Well, if you don't mind, I'm going to stand here to the side of the podium because I don't like feeling imprisoned by the podium. But nice to meet you all. My name is Stephen, and I am really honored to be here at RubyKaigi. This is my first time at a Kaigi. This is my first time in Japan, and it has already been a really lovely experience. You can find me basically everywhere on the internet as Fractaled Mind, and I write on my blog, fractaledmind.github.io. I'm here today because I love Ruby and I love open source. I've had the privilege over the last couple of years to be a regular contributor to Rails, as well as to the SQLite Ruby driver. And if you do know my name, it's likely because of the work I have done in the last couple of years to make the Ruby ecosystem the single best ecosystem in the world to build with the SQLite database engine. I had the opportunity last September to speak at Rails World about how Rails 8 and SQLite together can supercharge the experience of building web applications as solo developers. And if that's a talk that you haven't seen, it is on YouTube. In my completely unbiased opinion, it's great and you should watch it. And if it increases the view count, that's just a nice side effect. Today, though, I wanted to focus on pure Ruby and not web applications specifically. And I want to talk to you about the next project in my crusade to make Ruby the best ecosystem for working with SQLite. And that is a project I'm calling Plume. Plume is a tool set for working with SQLite elegantly. And what I'm going to talk about today is the heart of that project, which is a parser. You can find Plume now publicly available, open source on GitHub here at this URL. And what I want to do today is walk through why I am writing a parser for SQLite's dialect of SQL, how you can use Plume and how it works, and then talk about what's next and how you can get involved. So why would anyone write a SQL parser, let alone a SQL parser for just SQLite's dialect of SQL? And it's a pretty fair question, because if you did do some research, you would see that there are already a fair number of projects that are aiming to be a SQLite-specific parser across a variety of languages and frameworks and tool sets. And you would think that this incredibly niche market is already saturated. But the fact of the matter is that nearly every single one of these existing projects would fail to parse this SQL statement. And the reason why is right here. In well-formatted SQL, this would be a comma. But SQLite is perfectly happy to accept just blank spaces between table constraints. And if SQLite is able to parse something but a third-party parser cannot, that is a problem. And it's a problem because it limits the potential impact of that project. It'll never be as impactful as something like pgquery. pgquery is used in over 1,000 applications and packages. And the number one reason why is that it is the parser that Postgres uses, which means it has 100% compatibility. And that compatibility is the foundation that is needed to build an ecosystem of tools on top of a parser. When it comes to parsing, compatibility is king. If there is any SQL statement that the SQLite CLI will happily parse, but a third-party parser does not, that's a problem. And if there is a statement that SQLite would error on and the parser doesn't error on it, that's also a problem. We have to get to perfect compatibility. And so the question is, how do we get there, and what's sort of the state of things today? There are a couple of projects when I was doing initial research here that were pretty close. This one is a Rust-based parser generator that uses the exact same source grammar as this one is a Rust-based parser generator that uses the exact same source grammar file as the SQLite parser, but it has a couple of really key limitations. The first is that not every grammar declaration is supported. And the second, even bigger one, is that it regularly panics. So it is unable to be this foundational tool for the ecosystem to build on top of, as we can see in the number of projects that are using it. This JavaScript parser would actually successfully parse the example we gave at the beginning, and it has good momentum. There are over 300 projects that are using this, but it was archived nearly 4 years ago. So I think that there's a real need for this kind of project. And that's why I started Plume with this vision to build a foundation for the next wave of SQLite tooling. But if I'm being honest, this project didn't start with a grand vision for the next wave of tooling. It started with fixing a bug in Rails. I found a bug when I went to execute this migration. And the problem was that I wanted to define a virtual column with an expression that had a comma inside of it. And everything in Rails blew up when I went to run this migration. So I went diving through the source, and I found this line. Rails' active record SQLite adapter needs to understand your schema. And in order to understand SQLite schema, it has to do some parsing of the create table statement. And Rails uses some regexes and some basic string manipulation to try to make sense of things. So I found a pretty simple split on commas. Probably that'll just be comma definitions, but if you have an expression with a comma in it, all of a sudden everything breaks. So to fix this bug, I wrote this incredibly fun regex. I'm not even going to spend a lot of time on it. Don't read it. It's horrible. It fixed that bug. Even as I wrote it, I was aware of the other possible edge cases that would lead to very similar bugs. This is not resilient. And when I put this pull request in and got it merged, I was happy to have fixed that bug, but I couldn't help but daydream about what it could have been if I could have fixed the bug with code like this. Because if we did have a parser, and if we could inspect the schema of our tables and get back structured Ruby objects that were full and correct, it would make Rails' life so much easier, and these kinds of bugs would disappear. So this is why I wanted to start this project. I really do want to set a foundation for a new wave of tools for SQLite. It's obviously gained a lot of momentum here in the last couple of years, and I think that there's so much opportunity for tooling to come in the future years. And maybe, just maybe, we will be able to use this tool to secure Rails' introspection capabilities to drive active record when working with SQLite. And if I'm being honest, I wanted to challenge myself. I am a self-taught programmer. I never went to computer science classes, let alone get a full degree. I didn't really know much about parsing, and I wanted to, and this seemed like a great opportunity to dive in and learn more. So let's transition now to how you can use Plume and how it works. And to do that, we're going to look at a simple create table statement like this. Now, if we parse this SQL and we get the statement node, it'll look like this. And let's break this down bit by bit and see how the syntax tree is being formed and how we can work with it. So the create table token sequence is what is going to determine that we have a create table statement node. We see that the table we are creating is called users, so our node will have a name property or a table property that has a, let's look at this, table name node. The table value is our string users. Our first column is called ID. So inside of our columns array, we're going to have a column definition node. It'll have a name property. That'll be the string ID. That column is defined as an integer. So inside of that column definition, we will also have a type property. That type property will have a column type node that will have the text, integer, and it'll also tell us the affinity for that particular type. SQLite's loose typing system is fully supported here. We also see that we have a constraint on this column. So this is a primary key constraint with the auto increment keyword. So inside of our constraints array, we see a primary key column constraint node, and the auto increment option is indeed true. Our second column is called email, so we'll have another column definition node, property name, value email. We see the string is the type, another column type. We see the affinity. This actually has two constraints. It's a not null column, so we'll see that node in the column in the constraints array. And it is also a unique column. And so we have a second constraint node in our constraints array. This AST structure provides every single bit of information that we had in our SQL string structurally in a way that is easy to use in any Ruby program. And the parser is able to handle fully complicated create table statements. This is the most complicated create table statement I could write. And it would create a syntax tree like this. Pretty easy to follow. Yeah, I think we all get it. In order to support parsing large, complex SQL statements as quickly and efficiently as possible, the architecture is inspired by Aaron Patterson's talk that he gave last year at Rails World, where he broke down 3 key principles for parsing efficiently in Ruby. So the first is to write your parser in pure Ruby. You want to minimize the number of calls going back and forth between C and Ruby. So if you keep everything in Ruby and you allow YJIT to optimize, you're going to get speed improvements for free from the just-in-time compiler. You then want to minimize allocations. That means leaning on integers and symbols, which are objects that aren't going to allocate to sort of drive the primitives of your parser. And then when you do need to allocate, and obviously you are going to need to allocate some strings to make sense of what's there, you want to do that lazily. So only when needed do you provide the values that users ask for, and that's going to help keep everything as efficient as possible. So these principles drove the architecture for how Plume is implemented. It has a lexer. That lexer will work token by token, keeping track of the cursor offsets that are driving the tokenization process such that you can ask for a value if and when you need it, and only at that moment will we go and allocate that string and pull it out for you. That lexer is used internally by the parser. The parser is also going to work token by token. We do use a buffer so that we can peek ahead, so we keep track of the tokens. So the lexer can sometimes be 1, 2, or 3 tokens ahead of what the parser is looking at, but that's just managed easily with our buffer array. In order to make the actual parsing logic relatively maintainable, there are a number of helper methods that allow me to encode the grammar and all of the different flexibility that is logically required. And to sort of walk through how those helper methods are being used and how the parser itself is running, I want to walk through the create table statement parsing so that we all feel comfortable with how this gem is working, because I am going to ask all of you to come and help me and contribute, so you won't have any excuses by the end of this talk. If we look at the SQLite documentation, we will see a railroad diagram like this that really clearly explains the logic of parsing the create table statement. It is worth noting, you should be aware, that these diagrams are telling you how to write SQL. They are not telling you how to parse SQL. As we can see, they say you should put commas after table constraints. And SQLite is happy to allow you to not put commas there. And this right here, I believe, is the primary reason that most parsers have a number of incompatibilities, because their grammars are defined on these diagrams, and these diagrams are filled with lies. So buyer beware. If we jump into the logic for how we can convert this diagram into our actual execution, we will see, starting here at the beginning of the create table statement, this, where the first thing we're going to do is ensure that we have a create token, right? So if we expect that we are parsing a create table statement, we must have the create token first. So we use the require helper that ensures that that token is there and consumed, or we error. The grammar next says that we might or might not have either the temp token or the temporary token. That is why we use the maybe one of helper to say maybe we'll have a token, maybe not. And if we do, it'll be one of temp or temporary. So if either of those tokens are the current token, we consume them. If not, we just return nil and everything's okay. The next point is requiring the table token. As a small note, yes, you can just define a require method in your class or module and use it. Am I maybe writing not so beautiful Ruby because I'm overriding the require method? Possibly, but I like the way it sounds. So we do it. After you have a table, you might or might not have a sequence of tokens, if not exists. So the maybe all of helper allows us to check, do we have this exact sequence of tokens fully from start to finish? And if we do, consume all of them and grab the full span. But if we don't, just return nil and continue on. Next, we get the table name, and that calls out to a separate rule definition method that has all of the logic for getting the table name that might be qualified and structured in a couple of different ways. Structurally, you might expect that we would use a require helper method with a block to include the method. And that's actually what we do with maybes. If you want to check if you can parse another rule, you can call maybe with a block with the rule method. But in the case of requiring, this just adds overhead for very little value. So for rules that are required, we just call them directly. And I like to add a lot of spaces so things line up in a nice columnar way. If we shift our focus into the actual parsing of the definition of a table, we'll see the rest of our helpers here. So we can use the maybe helper to check whether or not the current token is the opening parentheses. If it is, we know that we are parsing a create table statement with column definitions. And you must have at least one column defined. So there we can use the require sum helper, which says there's one or more rules. In this case, we are looking at the column def rule. That is another helper method, a rule definition method. We're not going to look at its internals, but it includes all of the logic for parsing out a full column definition. And we tell the require sum helper that we are going to have those column definitions separated by commas that come after each definition. After we've collected all the columns, we look to the constraints. Here, there might be 0 or more constraints, so we use maybe some. In this case, the table constraints only are used inside of create column, so we don't need to extract it into a separate rule method. We can just define all of the logic directly in the block. And we specify that the trailing separator could be either a comma or nil. And this is, of course, the exact logic that we need to be fully compatible with SQL's handling of table constraints being either separated by a comma or not. So once we have collected all of the constraints, we must have our closing parentheses, so we use require one more time. And at the very end, we might or might not have a couple of table options, so we use maybe some once again. And that gives us everything we need to create our create table statement node, which, as we have seen, looks like this. Now, the only other final point to make is a small confession. This slide is a bit of a lie. This isn't actually exactly what the parser will generate. This is an abstract tree. The parser actually produces a concrete tree that keeps track of the locations and spans. But I personally find this a bit aggressive on the eyes. And so when you inspect the column or any particular node, you get back a lazy representation of the abstract version of that node. But you have full access to all of the span and location information. We just pretty print it for you. So as you can see, even the simple statement has a lot of information on it. You have access to all of that information, and if you wanted to or needed to use some of this fine-grained information, that's all there. But for the most part, we're going to keep it simple. Just to break down exactly how it's working, we're going to have these token spans that are composed of 4 parts. We have the tokens, one or more tokens, the start offset, the end offset. These are offsets into the original source string. And then the type of token that this is, this helps in some of the helper methods that are there to extract the value. In order to use these offsets, every single node includes a reference to the full SQL source string that was passed into the parser. And that is what allows us to lazily produce the values that are needed. So what happens in an IRB console, for example, if I just look at the node, it's going to access it, and at that moment it goes and lazily grabs all of these values to say, okay, what is the table name, what is the column name, the column type text. But in reality, you could write your tools on top of this, and if you didn't need any of that stuff and you didn't ask for it, none of those objects would be allocated. So The way that Plume works, this is a handwritten recursive descent parser. It is minimally allocating objects, mostly integers and symbols, in arrays. It works token by token, so there's never huge arrays in memory. The grammar is encoded with these hopefully very literate helper methods, and that allows us to produce a concrete syntax tree that we can then present to users as an abstract syntax tree so that you get the best of both worlds, the usability of the abstractness and the fullness of the concreteness. Okay, what is next? Well, I'll be honest. I didn't 100% finish it before today. So there are more statements to parse, and I would love for you to help me. I'm tracking progress here in the README. Now, I confess that this looks like I'm barely started. The truth is that create table statement is one of the most complicated statements that has a number of dependencies. So getting full expression parsing and select statement parsing, those two are like the hardest two. And then create table statement is the most useful one. And it allowed me to get all of the foundations right. And if you actually go and look at most of these statements, they're actually really easy to parse. So there are a lot of opportunities for you to contribute without having to go into very insane, difficult parts of the grammar. A lot of these statements are really straightforward and would be very easy to write the logic for using the helper methods. So I really genuinely think that all of you incredibly smart people could get involved and contribute to this project. But even if I am forced to do it alone, it won't take a ton of time now that all of the foundations are set. But I'm not trying to hide the fact that, yeah, there are more statements to handle. Luckily, create table statements, I think, are the most important feature, both for Rails and for some of the tools that I want to build on top of this. But if you have needs for parsing other statements, let's do it together. Next, I would also love any community help in hunting for incompatibilities, right? So as I said, if there's any difference between how SQLite parses a statement and how Plume parses a statement, that is a bug. And I would love that bug to be reported so that we can fix it, put it in as a regression test, and ensure that we get to full compatibility. Now, there shouldn't be many bugs with create table statement parsing because there are lots and lots and lots and lots and lots and lots of tests. I wrote a script that scrapes every single SQL statement in the public test suite of SQLite. There are, I don't know, 20,000 or so. And we parse all of those. And then I'm also handwriting tests for every single logical permutation of the grammar to get to 100% branch coverage. And so hopefully, when you go hunting for incompatibilities, you don't find many, but I hope you find some, and we can fix them because that makes the project stronger and stronger, and that is what we need to treat this as a foundational project for the ecosystem as it grows in the coming years. As those of you who were here for Marco's talk have already seen, he's much smarter and much faster than me, so he already built a web AST Explorer for his parser. That's something in the future for me, but if you saw his demo, you would see how incredibly useful that can be. You can put the SQL in, you can see exactly how the parser is going to make sense of it, and really get a feeling for how to make use of the parser to start building your tools on top of it, how you can get into the bits that you're going to need. So I look forward to stealing much of his code and porting it over to this parser. The other thing that I have been working on, I didn't have a ton of code samples. I didn't want to get into the implementation, but I do want to talk about the results, is using this syntax tree as the foundation for SQL generation. Yes, we have RL. No, I don't love it. And so I have been exploring some possibilities for different ways to bring the full expressive power of SQL to Rubyists without some of the object-oriented cumbersomeness of RL. So just to give you some teasers of some of the things that I've been building. This is a fluid Ruby interface to produce SQL, very much influenced by the SQL gem. And the idea here is that we can build the same syntax tree through Ruby and then have that syntax tree produce SQL for us. That will be incredibly nice. But more exciting to me is work I've been doing to define what I haven't yet named perfectly, but for lack of a sexy term, hash-based SQL, which is using structured Ruby primitives to encode the full expressive power of SQL in Ruby. And I think that this is particularly exciting because this bridges the gap for the biggest missing feature in SQL, in my opinion, which is composability. It is quite difficult, unless you're doing select statements and you use common table expressions, to compose parts of SQL together. SQL is just strings, and so you have to use the primitive tools available to you in any programming language that you're working with to compose strings, and it's brittle, and it's not particularly resilient to various kinds of needs that we have as programmers. But if we were able to encode SQL in a way that is literate, in a way that isn't burdensome or onerous on the eyes, but used Ruby structures, then you could imagine taking that hash that is the key of the value of the exists key there. We could generate that in a method. We could store that in a constant. We could build that up piece by piece across a module. However it's there, it can live in a completely different part of our code base, used in completely other SQL queries, maybe we just call it directly, or we can inject it as the value of this exists query, composing this smaller query into the larger query as needed, when needed, however we produce it. And the generation step to take that into full SQL using the AST is something I have been building as well into Plume, and one of the things I'm most excited to push to all of the edges of SQL. And the last thing for what is coming next is your contributions. I would love to see you in GitHub. I would love to see you open pull requests, to open issues, to submit incompatibilities that you have found. This is a project that has the opportunity to be vital to the emerging next generation ecosystem of SQLite tooling. And it's only going to be as strong as we all make it. And if it's just on my shoulders, it'll be mediocre. But if we all come together, it could be great. And so I hope that I have given you enough initial interest and confidence that you join me in this longer term project of helping to make Ruby the world's best ecosystem for working with SQLite. So find the Plume repository, give it a star, numbers matter, and I'm vain. Go to GitHub, and together, let's make this big, and let's make it real, and let's make it elegant, which is to say, let's make it Ruby. Thank you.